So this presentation is divided into two parts. The first part is about the attacks that we discovered in virtual reality applications. And the second part is more about the defenses that we designed against these attacks in a framework that we call MetaGuard, that stands for Metaverse Guard. And the speakers for today, as you may know, is my friend Vivek Nair from UC Berkeley and myself from TU Munich. We would like to acknowledge the NSF, the National Physical Science Consortium, the Hertz Foundation, and Berkeley Center for Responsible Decentralized Intelligence for supporting our work. Okay, so our research is closely linked to the metaverse, and probably during this Metaverse Safety Week, you have heard different definitions of what the metaverse is. If you talk with social media companies, they probably tell you that the metaverse is about connecting in new ways in virtual environments. If you talk with companies that are more into business, they might say that the metaverse is about collaborating with coworkers in virtual worlds. And whatever it might be, the truth is that the metaverse is not yet here, but they have a common denominator, which is the use of virtual reality. So our research is going to focus on looking into VR devices and see how much privacy they leak and how we can defend against these leaks. The reason why we went into study privacy in metaverse applications is because we are afraid that the privacy issues that we have today in the internet will transfer to the metaverse as well. And knowing that companies are losing a lot of money on selling VR devices at a loss in the hopes of recouping these losses through secondary revenue channels might indicate that, of course, data will also be valuable in the metaverse, and it might be misused. So that is why we looked into how much privacy are we going to expose in metaverse applications. Okay, so we have to first look at the metaverse from an adversarial perspective. This is common practice in info security. And we identified 4 types of attackers. We have, from left to right, the hardware attacker, which controls the firmware and manufacture the VR device. And it has access to the raw sensor data itself. Then moving on, we have the application that is running locally at the client. And this attacker has access to the API that the VR devices provide, and therefore it also has access to the raw sensor data and other information that the VR device generates. Now, if you are playing a multiplayer game, then there will be a server that is ingesting or receiving this information from your application. Therefore, it has access to this data as well. And then it will relay this information to other users so that they themselves can render the avatars of everybody in the VR game. So the users that are playing the game will also have access to your telemetry and other information. And not only this last attacker is able to interact with perhaps the victim and could perform even social engineering attacks, right? And 2 things to note here is that from left to right, the data fidelity will degrade as data is being processed, like, for example, compression. And also, 2 attackers can become one and become, therefore, a stronger attacker as well. Okay, so with this framework is the lenses through which we look at privacy in virtual reality. Okay, so with this framework, we conducted our metadata study that stands for Metaverse Data. And what we did was to design a game that is based in an escape room where players will have to find out the password of one room to move to the next room. And there were a series of rooms that we designed with puzzles and other things they had to do to prompt the user to do certain things that might reveal certain information. And it was just 2 of us. So you could imagine that bigger groups of developers could design games that hide artifacts to reveal information more easily than we did. So we had 30 participants play our escape room game. And after they gave us their consent, we collected the data of their playthrough. And then after all our participants played, then we analyzed this data that they produced in virtual reality. And we analyzed the data and we tried to see if we were able to figure out their ground truth. The closer we got to the ground truth, the more successful the attack was. And this was in essence what we did. Basically analyze data and see if we were right in the analysis. So this was what constituted the metadata study. So now Vivek will try to do a VR demo, and I will discuss the different things that we were doing in this game. So hopefully it works out, and otherwise we will go through the slides. So he's gonna go into the metaverse now. You are muted, but okay. All right, so he's in there already. You can see the first room. This is just an introductory room where it says hello. The password is hello. For example, it's just to get the user to understand the mechanics of the game. So Vivek is donning the VR headset, the controllers, and we will move on to the next room. So the first rooms that we designed was just to get a hang of it. So face was the password of this room. Velvet was the password of the next one. And now we enter into the rooms that you had to interact more with. So this room had different letters on different screens that they spell out church, which was the password of the room. And again, these rooms in the beginning were just to get habituate the user to virtual reality and the mechanics of the game. So this is the first room where we are actually extracting useful information. So if you're familiar with colorblind tests, these screens have these palettes, and if you are colorblind, you are potentially not able to read them. If you're going quickly through this room and you're not colorblind, you might not notice this, and otherwise you would not be able to solve this puzzle, releasing one data point. If you move on to the next rooms. Okay. Okay, this room is again part of what we also assessed, which was the Montreal Cognitive Assessment Test. I don't know if you are aware of this one, where it's a test to discern whether or not a person has dementia. So throughout these rooms, you didn't notice, but there were passwords, and these passwords you had to remember. And then this room, in order to pass this room, you had to recall these passwords, and then you would say the word that is highlighted in yellow. So we were also measuring your cognitive ability here. This room is also fun. We prompted the user to do different shapes with their body so that they would reveal the wingspan. You see the third figure, which is extending its arms, and in that moment, our algorithm would capture how long the distance between your arms, and therefore you can fingerprint. You have a biometric that you can fingerprint. Of course, height is an obvious one. If it's just in short the maximum Y coordinate of the VR headset, and therefore you have like 2 fingerprints already. You have the wingspan, you have height, and we also, as I mentioned before, we already collected color blindness, and we already collected the cognitive assessment that you through those puzzles. This one is about physical fitness. Of course, Vivek is not going to do this, but going up and down, how deep you can go in your squat will determine how fit you are, and one had to go up and down to reveal the different squares. Okay, we can move on. All right, this was just a cipher. This is a filling room. Then we had this, if I recall correctly, was reaction time. So it's very laggy when you are like presenting and at the same time using this. The computers, they might lag a little bit. Okay, this was for reaction time. So we actually got another biometric where you had to press a button to, as soon as something changed its color. Okay, this one is a very interesting one. The password of this room is Apple, and you see the word Apple in different languages. So when you say Apple, looking at, for example, pomme, then you could infer that the person speaks French. It's not exact, but again, this is part of the inference that we do. So it's more behavioral rather than observational. This was another filler room. This one is interesting. So imagine an attacker presents user different objects that are moving, and depending on the pattern that the user recognizes, you can actually tell what is the frame rate of their device, because different devices have different frame rates depending on how expensive they are. This is part of the cognitive assessment test. This is also part of the cognitive assessment test. Likewise here, I think, yeah, again, the cognitive assessment test makes you redo these memory tests again and again. These are more of the same assessments. Yes, and these we are coming to the end. These are more obvious, like eye tests, for example, that could be hidden in other ways. And this is for long-sightedness, and this is for short-sightedness. And this was the last part of the room. If they were able to read this, then you could tell how well they could see. And then this was at the end. They finished the game, so they could see all the rooms that there were, and then you can see like let's say this was the end scene basically. So you could see that it was kind of clunky. Of course, it was just two developers doing this, and we just wanted to prove a point. And the fact that some of these attacks, you might see that they are very blunt. Perhaps a bigger group of researchers was not able to, would be able to hide these artifacts to extract more information better than us. Nonetheless, this was just the tip of the iceberg. We were collecting in the background other information. So you can see the example here of height, for example, and the wingspan that we already saw. You can move to the next slide, Vivek, if you may be so kind. This was the reaction time that we saw, and also the frame rate. This was the eyesight test that we had as well. And this is the one that I mentioned about Apple, which is basically where you are looking at. This is another. We didn't have an eye tracking device in our VR setup because commonly they don't use it, so we want to be as general as possible. But there will be more attacks that you can actually carry out in the metaverse depending on where the person is looking. So, for example, you could see it in advertisement where if someone is looking at a Coke instead of a Pepsi, then the person is the person will be more interested in Coke, so you can advertise more heavily into that product. And then you can even think about more pervasive things to do, like religion, politics, etc., just of where they are looking. So that is very, very pervasive as well. This is the experiment setup. So we had a large play area. We had 4 fidelity motion sensors, and then we also had tracking sensors, and we also have 3 cameras, the proper lighting, a microphone, and then we had an observational area. We were like helping the user, the participant, and so on and so forth. There are other attacks that were not that were happening in the background, as I said. Some of them were maybe kind of obvious to you in hindsight, but there were other things that were happening in the background. So, for example, we could actually tell at a state level where were you with multilateration. You could ping different servers, and then you can measure the latency, and based on that, you can triangulate where the person is. So these attacks also apply to virtual reality, not to only mobile phones or other applications. Also, you didn't see this, but we were keeping track of the coordinates of your headset. So we actually were tracking how you moved in your room. And if you just take the maximum and min coordinates, you actually can tell how big the room is. And this is another fingerprint that you can put attached to the user. So finally, we actually collected more than 25 attributes. These are the most important ones. You can see that we were able to extract height with high accuracy, with 100% accuracy within 7 centimeters. Also, we were able to tell which arm was longer, their interpupillary distance, so what is the distance between their pupils, their wingspan also with high accuracy, 86% within 7 centimeters. Their room size had also high accuracy, their geolocation. We also got different VR device specifications, even their handedness based on observations of what hands they used, their eyesight, whether they were colorblind, the language they spoke, their physical fitness, their reaction time, and whether or not they had dementia, right? So through the gameplay that you just saw, you might have noticed that perhaps there were maybe a few data points that you could gather, but if you look really closely, there are very, very many. And one of the important things to consider here is that for every new attribute that you have, there's a new chance for an attacker to fingerprint you, right? So out of the 30 people that we had with just 2 attributes, height and wingspan, you were able to uniquely identify that person within the 30. So of course, if you're going to have more players, like 500 or thousands, then you will need more attributes. But the fact that we were able to gather this information with high accuracy, and there are so many, that you are able to, you could potentially be able to identify these people amongst large clusters. For example, there is a study that has some decades that says that you could actually identify any person in the world with 30 attributes based on their demographics. It is true that our demographics, this study doesn't, all of them are not demographics. Nonetheless, there are unique attributes that you could attach to everybody, and in combination, you could identify people potentially across the world. Now, these attributes were, can you go back to the previous one? Sorry, thank you. So these attributes were important. Nonetheless, they are more pervasive ones that you can actually gather from these primary attributes. So we actually infer gender, age, and ethnicity with with 100% accuracy. Surprisingly, age within 1 year. And this is just based on the attributes that we previously gathered. So you could input into a machine learning model their voice, right? And that will tell you very high, with high accuracy, what the gender is. For age, we use primarily how well they could see, their height, and their physical fitness. And that could tell you age very well, and ethnicity based on accent. So there are things that are on the background that might not be intuitive. Like you wouldn't have told that from the demo that Vivek did, and nonetheless, you can actually gather this. Now, these studies have had a lot of, have received a lot of attention from Forbes and the Register, indicating that the public is really interested in this, and that everybody thinks that this is a crucial problem that we have to focus on. And feel free to go through these articles, because they are fun to read and they explain our research very briefly. So I'm done with my part of the talk. Now Vivek will continue with how to defend against these attacks. Thank you.
Yeah, so just to summarize, right? So the point of our first study that Gonzalo has summarized well here is not exactly about these particular attributes, right? This is neither a totally exhaustive list of attributes that you can observe in VR, nor is it particularly interesting on its own, right? So a question you might have, for example, is why do I care if someone can observe my height in VR, right? They can do that in real life anyways. And the point, as Gonzalo highlighted, is not just that these attributes are available to parties in VR, to applications, to servers, even to other users, but the fact that they can make inferences based on them. So the fact that not only can they hear your voice and measure your height and wingspan, but also that when you input those things into a machine learning model, you can accurately get your gender and other attributes, demographics as well, and in fact, de-anonymize you. So that's one of the main findings, is that you have so many attributes that you can accurately make these inferences about users. And the second main thing I wanted to highlight for a second is just how much power an adversary has once they can construct these environments in an adversarial way. So not just passively observing users like previous studies have done, but actually manipulating the VR environment in a way that seems like a fairly reasonable escape room style game, with these puzzle-like elements that users are motivated to solve. But actually in the background are revealing information. So once you can construct the environment in a targeted way, you can get users to reveal a lot more information without necessarily knowing that they're revealing information about themselves. So those are our two key takeaways from this first part, that VR can be manipulated, gamified to steal more information, and that those attributes that you steal can be used to make inferences about your demographics and indeed your identity. Unlike the platforms we're used to, like the internet, the web, where we have privacy tools, we have proxies, VPNs, we have incognito mode. We don't really have this in VR right now, right? So we don't have the tools as users to counteract these attacks on privacy if we're not comfortable with them. And so the second part of this talk is going to be attempting to solve that problem and present some countermeasures to the privacy risks that we just highlighted. And specifically, the way we do this is with a tool called differential privacy. Differential privacy is a statistical quantification of privacy. So it's a privacy framework that allows you to give a numeric measure through this parameter called epsilon, a numeric quantification of how private data is. And it does this by essentially saying how hard is it for an adversary to differentiate a data set with or without a particular data point, right? And so this epsilon parameter lets us give a rigorous approach to counteracting these attacks by, when we present countermeasures in this section, we can actually measure their accuracy in rigorous statistical terms. So the two specific differentially private tools that we use to counteract these attacks are the bounded Laplace mechanism, which we use for continuous attributes, and the randomized response mechanism, which we use for binary or Boolean attributes. So things like handedness, where it's left or right, and so 1 or 0. We use a randomized response, which is based on coin flipping. For everything else, where you have a continuum of values, the bounded Laplace mechanism, which is based on a Laplacian noise distribution, has this nice property of guaranteeing minimum error for a minimum mean squared error for any given privacy value. So our approach in this section is going to be to use these functions on various data attributes to protect your privacy in VR. In other words, to limit, in particular, the ability of adversaries to make inferences based on your data. And we want to do this in a way that maximizes privacy, but minimizes your impact on your user experience. And so the mechanisms we chose and the framework of differential privacy has this nice property of being provably optimal in this trade-off, giving you the most privacy you can get mathematically for a given amount of usability impact. And so that's sort of how we frame our defenses as being statistically optimal with these two mechanisms. And so when we implement these, we have a picture here of me standing in a Metaverse environment using our implementation, differentially private incognito mode implementation that we call MetaGuard. The reason we call it incognito mode, to draw a similarity to something that people are already used to in web browsers, private browsing mode. And the goal of this MetaGuard plugin, which we've released now as a Unity plugin, it can be added to any existing Metaverse application with a fairly limited number of exceptions, with the fundamental goal being to prevent you from being tracked across sessions. So one of the biggest problems, as I mentioned, with having all this data that adversaries can gather about you without your knowledge in VR is that they can uniquely identify you, right? It's very unlikely for these 25 to 30 attributes that any other user has that exact combination of attributes, right? And therefore, even if you think you're anonymous, someone can watch you for a while, gather this data and pinpoint exactly who you are, right? And incognito mode on a browser has the goal of making that impossible, making it harder to track you from one session to another. And our VR incognito mode has the same goal, making it harder to pinpoint exactly what your identity is by making it harder to get these attributes that are then used to fingerprint you. But just to look at the usability standpoint for a second, because this is an important aspect of any privacy research, is that our users who are not privacy experts going to be able to use this tool effectively, right? And so, this at a high level, it's one click, right? This master toggle switch is all you need to do to enable MetaGuard and the defenses, right? So with one click, you can turn on this incognito mode in the metaverse and get these corresponding defenses. And I'll talk in a second about what these defenses are actually doing. But if you're a user who wants to dive in deeper, you can also choose which actual attributes about yourself you want to hide and which attributes you're okay revealing, right? And the reason you might be okay revealing some is for application-specific usability. For example, if you're playing a game in VR like Beat Saber, where you need to use your hands very precisely to touch objects or to interact with objects, then you may want to turn off this wingspan and arm length defenses so that your hand precision is maintained, but you might not care as much about your height or squat depth being exactly accurate. So if you have some application-specific needs, it was important to us that you can tweak which attributes this MetaGuard is affecting according to your needs. And then lastly, I mentioned earlier that we have this privacy parameter epsilon when we're using differential privacy. And we actually have a slider here where users can change that value depending, again, on their needs. So in an application like VRChat, where you're just talking to people, interacting, then you could put this slider all the way up to high privacy, and that would maximize your anonymity, maximize your attribute values. You would lose some precision by doing that, right? If you're doing something like, on the opposite side of the spectrum, competitive gaming, where you don't need to have total privacy, you just want to not be exactly identified, then you could move this to the low side, where you get almost unnoticeable impact on your usability. And so, we have tried to strike the right balance here of making it very easy for users to go incognito, to get additional privacy with the click of one switch, but also dive in and tune their experience to their needs if they wish to do so. So, okay, so how do these actual defenses work? So we talked about the underlying statistical tool of differential privacy. So when you toggle on a defense, what's actually happening, the first thing that happens is your device takes a snapshot of your instantaneous ground truth attribute values. So for things like IPD, arm length, wingspan, the size of your room, your height, etc., right? So you get an instantaneous one-frame snapshot of these values. And what happens after that is that you use this bounded Laplace mechanism to sample a noise distribution centered around your ground truth values, right? So this is why you need the attribute values, so that the offset, the protected attribute values, are as close as possible to your real values, minimizing the impact while still being within a differentially private distribution. Once we have calculated these values and the corresponding offsets, so the corresponding private values, our plugin goes into the virtual game world. It looks at these virtual objects. So for some context, and this may be repeat information for some of you, but the way a VR application typically works with something like Unity is you have the OpenVR or OpenXR API streaming telemetry data into the game engine, into the Unity game engine. And the game engine is inserting these virtual objects like the left hand, right hand, head into the game world to mirror the positions of the telemetry data it's receiving from the OpenVR APIs, right? And so what our application does is it inserts these intermediate objects, these 4 offset objects, into the game hierarchy. And it sets up these coordinate transformations between the native VR objects and the coordinate origin. And so it's inserting these intermediate offsets and these transformations according to the offsets we calculated earlier. And all you need to know about this is the effect of these coordinates, which are simply position, like offsets, and scales. So changing the sort of location or scale of these coordinates of these objects. The result of this set of transformations is whatever set of switches you have flipped on as the user, the observable locations of those objects will now match the noisy, the private attribute values rather than the intrinsic or the ground truth attribute values. So that, the reason you need this set of transformations in this hierarchy is to make sure that any possible permutation of enabled defenses enforces exactly those private transformations and nothing else. And so specifically, we have two types of offsets. This is one of the tricky problems with doing privacy in VR, is that the simplest method of just shifting coordinates in order to anonymize certain data points on certain axes is actually problematic, right? Think about something like height, where, if I were to just add a fixed offset to my height, when I'm standing up, it would maybe be a valid method because you would see my height plus this offset, you wouldn't be able to observe my true height, right? But now if I need to go close to the floor for some reason where my height is 0, you'd still see this offset. And in fact, now you would know my real height after that, because you would be able to subtract that back from what you observed previously. And so this is why we use, scaling, in other words, warping the virtual world, warping the coordinate axes as one of our main techniques, so that the 0 point for these attributes is preserved. Another thing you can think about is wingspan, right? The distance between your controllers. So you want it to be private when your arms are extended, right? But you still want your arms to touch in the virtual world when you touch your real hands, right? So you can't just add something to the distance where you lose that 0 point. And so this is the reason for these dynamic or multiplicative offsetting approach, where all of your coordinates maintain their 0 point, and therefore you preserve those the user experience when they you preserve the way users expect the virtual game objects to behave in essence. And so the result of these transformations, is shown here. So when what we did, we took the data from the 30-person user study that Gonzalo had introduced, and we reran that. We replayed all of those recordings, all of those users' usage sessions, play sessions of the escape room. This time with Metaverse, with MetaGuard enabled in the virtual environment. Right, and then we reran all of the attacks on top of that with MetaGuard on and MetaGuard off, and also sort of at each of the supported privacy levels on the slider. And what we found is that even at the lowest level, with relatively imperceptible user experience degradation, you have a significant impact on the ability of adversaries to infer data attributes of a user. So if we look, for example, at things like height, which were 100% accurate within 7 centimeters without any defense enabled, right? Immediately you drop to less than 70% even at the lowest privacy level, and all the way down to less than 40% at the high privacy level. I won't go through all of these, but I'll just say that there's a significant reduction in the ability of adversaries to infer these attributes when you're using the extension. Recall that these inferred attributes are based on adversaries collecting all of these data points and then running a model on top of them to make inferences about a user. So even though MetaGuard, the extension that we mentioned, doesn't do anything to directly protect your gender, for example, right? The fact that adversaries cannot infer things like your height and your wingspan as accurately as they could before means that they cannot use those data points to infer your gender as accurately. And so if we look at this bottom table here, we see that these inferred attributes also have a significant degradation in accuracy. Most importantly, if we look at identity, the ability to uniquely point out which individual you are in the metaverse based on your unique combination of attributes, which was 100% accuracy without MetaGuard enabled, right, is less than 6% of the time can you do this at the lowest privacy level of MetaGuard. And the point is that by degrading all of these attributes just a little bit, right? Because you need to combine many different attributes to identify a VR user, when you degrade all of these a little bit, your ability to point out who you are exactly gets significantly degraded, gets significantly impacted. And so if you just care, if you don't necessarily care about people knowing your height and wingspan, but you want to make sure that they can't point out exactly which individual you are with any degree of accuracy, then a very low privacy parameter, a very low amount of noise with the MetaGuard extension, putting that noise in the right attributes has a huge impact on the ability to identify a user. And so that's one of our most interesting results, is that you don't need much noise with MetaGuard to totally throw off the ability to de-anonymize individuals.